Hello, everybody. I would like to welcome all of you, at least in this online forum, to our first workshop, which we have in the new project, which just started 1st of January. I hope that you are all fine, despite the limitations which we have by the COVID. I hope that personally you, your families, your friends, your students are all fine. And yeah, like it will be much better if we meet face to face, if we could discuss at our faculty and enjoy a nice atmosphere. But yeah, like we are limited by the current situation, still limited. We discussed quite a lot whether we should move this workshop forward and wait until the moment when we could all of us meet. But then we decided that we actually will not do that, that we will somehow face the situation and all limitations with COVID, and we will make that workshop online. As well, we thought that, yeah, it's quite nice chance to, when we can't travel, to exchange what we did over last practically 2 years, where we are limited in the traveling. Means I would like to first thank very much to Petr Marek, Petra Zabishova and Alisa Manukova, because they did a lot of work to prepare this online workshop, and it will never ever be possible without them, because yeah, like I am already quite busy by many other things. It means I very much thank you them for all that help in the new grant which we have. And that grant is actually quite special type of grant from European Union. The official title of that project is Twinning in Non-Gaussian Physics for Quantum Technology. It belongs to still to the program H2020, which actually was already closed. And right, I can't go further. Now it works perfect. It belongs to the
You're muted, Radim.
Yeah, thank you very much, Julian. Yeah, it belongs to the call which is called widespread, and this call is actually for new members of European Union. Although we are not anymore so new member, it's still for us, and it allows us to strengthen together with the other established research places in Europe to strengthen our research further and to make new networkings, as you will see, and in general to contribute for a more balanced distribution of research facilities and as well excellent researchers over the Europe. It belongs to the CSA, coordinating and supporting action of H2020. It will run for 3 years. And as I already said, it started this January. It's quite a well-supported project, as you could see here. It's not directly supporting the research facilities. We can't pay researchers, we can't buy new experimental equipment, but we could do a lot of other activities. And to build that project, it's as I said, it's important that one team is actually from these widening countries like Czech Republic, but as well it could be the other country. I hope that by this I could inspire some colleagues to apply for such a project. And then you need at least 2 partners. And after some discussions we agreed with Ulrich and Julian that they will be partners in this twinning project, and they will help us to improve a couple of points here in OLOMOUC, but as well, we hope very much that our young researchers and our experience and long-term collaboration will actually contribute to research in their laboratories. Means there are major points which we could support by this project. And I think some of them are very relevant to the general quantum information and quantum technology society. It means the main one, I would say, which is important for us in OLOMOUC, is that we would like to very much broaden the research profile in modern quantum science and quantum technology. We would like to enhance chances to enter the new fields, the fields in which our researchers never worked before. And this twinning project is an excellent tool to actually execute that. The other thing which we would like to improve in next 3 years is the networking with the top quantum technology laboratories, because our field changes quite dramatically from quantum science more and more to quantum technology. It means there are new laboratories which offer new possibilities, but as well new technology, but as well they are in the fields where we have a limited experience. It means that we would like to enter to these new networks as well. And on the scientific side, precisely on the scientific side, we would like to improve and broaden the applicability of our theoretical research in non-Gaussian quantum physics. We recently do as well a bit more in experimental research, as you will see in that field, but still our main capabilities are in the theoretical and are on the theoretical side. And we would like to broaden the applicability of the research which we do here in the theory to the new directions and the new platforms of quantum technology. And of course, last but not least, we would like to disseminate more intensively all the outcomes we will achieve, and we achieved already, to the scientific community, and to possibly communicate about this as well to the general public. And mainly, and I believe that's very important, to young generation, to high school students, which potentially could be in short time our collaborators and people which will take over our research at some point. To run this project, we need team which is already experienced and team which is solid and which can contribute both on scientific side, but as well on the organization side. And we already have such a team. The team consists from practically 4 or 5 people responsible for the different tasks in different work packages. For work package 1, which is mainly about the training and collaborative process by which we try to exchange experimental and theoretical knowledge between OLOMOUC and our partners. For that work package, Vladislav Usenko is responsible. Then there is a second work package, and right now actually this event is part of that second work package. This is a work package about the workshops and summer schools, and that one will be mainly controlled by Petr Marek. The third work package, which is about the broad transfer of knowledge and expertise by expert visits, and as well by our presentations on international conferences and colloquia. That work package will be actually in the hands of Ondřej Černotík. And then, of course, not negligible part of any of such a project is administration and aspects which are connected with dissemination and communication to general public. And for that is always good to have very strong administration team, and this is in our case Petra Zabishova together with Jarka Kolashina. Like things which on the scientific side, this project plan to deliver are the new experimental proposals which will likely not only come to Lyngby and Paris, but they will as well come to other places from our theoretical team. We want to as well prepare for younger researchers a couple of reviews about that field of quantum non-Gaussian physics. And we want to as well strengthen in the grant applications and fellowships for young researchers. It means these are things which you could expect from the Non-Gauss project. And I think you are mainly interested in the international events, which you can then attend and enjoy together with us. It means today and tomorrow and day after tomorrow, we have online non-Gauss workshop, but there will be plenty of the other events, which will be in OLOMOUC, in Denmark, in Lyngby, but as well in Paris. And yeah, you see that there likely will be the full, not online, normal workshop this autumn here in OLOMOUC. The reason is because we got funding for organizing of this workshop, for people to come and to accommodate them, and then it will be of course silly to give that funding back when we can use it for an I-7. It means this is what is planned for this autumn. We all hope that COVID will disappear completely and we will be able to meet here. If not, then we will move that workshop to another years. Then another plan still for this year, or maybe beginning of the next one, is something like a Christmas school in Denmark. I think that could be particularly attractive in that beautiful country, in the place like Copenhagen or Lyngby. And then there will be gradually other workshops in Paris next year, then summer school in OLOMOUC, then another workshop in Lyngby, then spring summer school in Paris in 2023, and then final workshop in the same year, which will then conclude that 3 years project. It means I think you can look forward to all these events where we will quite intensively and as well quite frequently exchange what is new in our field. And we all hope that actually that will very much contribute to advance our field. And after the 3 years, we will know much more than before, and more of the theories will be tested in the field of quantum non-Gaussian physics. It means this was something what I wanted to tell about non-Gauss, but of course I would like to as well a little bit update you about just few points from our recent results. And therefore I decided to add a bit of the scientific talk to that introductory one and extend these non-Gauss to a bit of description about new aspects of quantum non-Gaussian states, which we both investigated theoretically, but as well there are new experimental results in that field. You see, instead of the long list of the name, there is just a short word non-Gauss team. This is because the number of people which are in OLOMOUC interested in quantum non-Gaussian physics, in quantum non-Gaussian states, is already quite large. Of course, all of them, they don't do the same things. Their interest is quite diverse, starting from the basic research about quantum non-Gaussianity and ending by the applications of that in quantum communication, quantum sensing, but as well in new fields like quantum thermodynamics. It means it will be very hard to present all contributions from these people, both theoreticians and experimentalists. Therefore, I will just focus on few examples which I selected. Of course, that field will not rise well without experiments. And in OLOMOUC, over the last years, we were able to improve our experimental facilities, going from the experiments with the single photons to experiments with the quantum states of trapped ions, and as well with light emission from hot rubidium atoms. It means we already extended our experimental facilities towards quantum states and quantum non-Gaussian states of matter, but we hope that that will actually quite intensively continue and improve over the years. Yeah, like we will never ever have all experimental platforms at one point. That's very expensive and more or less impossible. And therefore, we are very happy that we keep and enlarge the experimental collaboration with the laboratories, not only in European Union, but as well outside, overseas. And I think during the workshop, you will hear about that in a couple of talks and a couple of posters. Mainly, I think you will hear about the collaborations from Lyngby and as well from Sorbonne, and definitely from Akira, from Tokyo. It means, yeah, this is what is already quite well-established network in the quantum non-Gaussian states, but we try to go further and even extend this network. We started basically last year the collaboration with Yale University, and we would like to very much push further the collaborations with the new places where they have experimental facilities which we don't have here in OLOMOUC, and therefore we can by working together we can learn quite a lot in the new fascinating field of quantum and Gaussian physics. Then I thought how to kind of visualize the situation in quantum and Gaussian physics with quantum and Gaussian states in these days. And I came to idea that maybe good to emphasize is that we actually have like two quite dominant poles of very different quantum non-Gaussian states. One pole, let's think about this like the North Pole, are states which are quantum non-Gaussian because they are pretty much limited in the FOCK-STATE basis. It means these states are like superposition of finite number of discrete FOCK-STATes. And because of that, they are by definition quantum non-Gaussian. They are very hard to simulate by the Gaussian states, by their mixture, because that mixture is always in a finite tail in the FOCK-STATE. But there are as well other states. We can think about them that they are kind of on the South Pole, and they have very different nature. They are rather superpositions of continuous variable eigenstates of position, oppositely to the discrete states here. But then the coefficients of that superposition, the amplitudes of probability, they can be in simplest form written in just this exponent of some function, which if that function is quadratic, actually brings quantum non-Gaussianity to these very different class of states too. Of course, these are, as I tried to visualize, just two extreme points, two extreme poles of the globe. And of course, there are many states here and there and there and there. And they have very different natures. They are kind of combinations of both of these aspects. And they can be quantum non-Gaussian in a very different sense. But they can therefore be very useful for various applications. But right now, we are rather covering only very little part of that space here at this globe. We don't know so much about these states. We know a bit more about these ones than about that ones. But I hope that in the upcoming years, we will be able to learn much more and to realize the experimental potential of these states, and as well their possible applications to improve quantum technology. It means in the next slides, I will focus rather on that discrete form of quantum non-Gaussian states when we have that sharp end of the distribution in FOCK-STATE basis. And to start, I think I should remind to all of you that there are already rising applications of these superpositions in various corners of quantum technology, in quantum sensing, as well in quantum error correction. These states, they became more frequent for quantum communications and quantum connections. There are as well considerations of these states for quantum computing, for some primitives of quantum computing, but as well they could fit quantum engines, and we can think about them in the sense of quantum thermodynamics. And certainly there will be more and more applications once these states are more and more prepared in various laboratories at diverse experimental platforms. But these superpositions, they are superposition of some building blocks. And although the FOCK-STATEs are here in quantum physics already for many decades, I was personally very surprised that there is still a space and a lot of unclear points about them. And yeah, it brought us actually to their quite extensive investigation. Yeah, as I said, they are quite frequently discussed in the literature. These were states which were already the beginning of quantum optics. It means it's not surprising that they were the examples of non-classical states which were broadly investigated over the last 50 years of quantum optics. And I think this kind of slide is not basically anything new for anyone in the audience. It's just the repetition that non-classical states are these states which are incompatible with the mixture of coherent states, as it was introduced by Roy Glauber and others. And if you think about the simplest experimental test, how to verify such a non-classical aspect of, for example, single photon states, then we can think about the test of second order autocorrelation function, which is known as a G2 function, using quantum modifications of Hamburg-Brown-Twiss experiment, means HBT experiment. And then in the literature, you can find a very simple condition when such states are non-classical, written in the terms of probability of the single photon and probabilities of two and more photons. Means this is just about the non-classical aspects of the single photon state. But if you think about quantum non-Gaussianity, that condition actually changes quite interestingly. There is not only change in the prefactor, there is as well very important change in the power of probability of the single photon state. And this is what basically we found out a couple of years ago And it stimulated a lot of research, not only in the theory, but as well in experiments. We actually tested possibility to see such a single photon non-Gaussian states, even after some quite extensive attenuation. We tested that here in OLOMOUC in 2011. And then there was in parallel another test which was published in 2012 in LINCB, which was done with the homodyne detector. Instead, here the test was with HBT measurement. We observed quite safely that quantum non-Gaussianity is detectable using basically at that time quite ordinary source of single photon states. But yeah, we were interested whether this is not just the specific feature of these experiments with parametric down conversion, whether we can see quantum non-Gaussian states as well as other experimental platforms. And one platform which was particularly interesting for us was emission from solid state quantum dot sources. We were able to observe quantum non-Gaussianity from these solid state source in heralded way. And right now we try to detect some similar features without the heralding. It's quite demanding, but we already know that at least in heralded way, it's detectable from solid state sources. And then we tried as well to see quantum non-Gaussianity from the emission of the single atom. We as well succeed that despite very low emission rate and very low collection efficiency. And both these experiments, they were done in Innsbruck. But we as well progressed in our lab to generate quantum non-Gaussianity from atomic sources. And you can visit poster number 8 tomorrow and hear from Jaromír Mika the details about that. It means this is still ongoing research, how to see quantum non-Gaussian states, quantum non-Gaussian single photon states of light from such a different atomic sources. But we didn't stop in the theory on that. Our intention was to find actually hierarchy of quantum non-Gaussianity for these FOCK-STATEs. This is something what is very limitedly possible if we think about distinguishing the FOCK-STATEs using just the profiles and negative values of the Wigner function. It means we thought about such a simple detection method in which you, from the light source, you basically receive on some multiplex detector or multiplex detector, you receive some portion of light, and you are able statistically confirm that actually your state is distinguishable from some trivial states in that hierarchy, which are always below some threshold. It means mathematically such a definition of the hierarchy can be visualized here. You see that the formula, which looks maybe a bit more complex, but it's actually quite simple, is consisting from 3 parts, from something what we could call like core state, which is sandwiched by displacement and squeezings, which are both Gaussian operations. And the coefficients of these Gaussian operations, they can be mixed in arbitrary way using these classical probability distribution. It means here you put something what defines your core state, and based on that you jump in the levels of the hierarchy, and these core states, they can in addition be squeezed and displaced anyhow, and all these contributions could be mixed with various weights. It means that basic non-Gaussianity is that very simple case when that core state is just vacuum, and by that we exclude any squeezed displaced vacuum. It means any Gaussian state. The second level of the hierarchy is a little bit more sophisticated. The core state is actually arbitrary superposition of FOCK-STATE 0 and FOCK-STATE 1. And these superpositions, they can be additionally displaced and squeezed. And all these possible states you could mix as you like. And by that, you could gain states which can have they can have very diverse Wigner functions. They can have negativities distributed in various ways. But apparently, if you have FOCK-STATE 2, the ideal FOCK-STATE 2, you will not be able to write this as this kind of state, or as well not as any mixture of that state. It means you can, if you find the threshold for all these states, you can distinguish something like genuine FOCK-STATE 2, and we very much look to that and extend this as well to higher levels, not only second level, but as well in general nth level, when this state is actually such a superposition up to n-1 FOCK-STATEs. That problem was quite intensive analytically. It was very, very hard to solve it, but at the end we were lucky, and together with Lukáš Lachman, which did a majority of work on this during his PhD study, we came up with even analytical formula, which in a very important corner for many experiments, in the corner when basically all probabilities except the probability of vacuum are rather small. In that corner, it gives quite precisely the threshold which we need to basically surpass to observe these genuine quantum non-Gaussian features according to such a hierarchy. What is important here is that this evaluation, this hierarchy particularly, goes beyond the Wigner function and formalism and the evaluation of the negativities of the Wigner function. And actually, it happens in the two different ways. First, the hierarchy allows to observe states which could be quantum non-Gaussian, and they could jump up in that hierarchy, even if the losses are larger than 50%. It means then you see only positive Wigner functions at your detection setup, but still you could test this hierarchy. And second thing, which is as well remarkable, is there is no hierarchy like that just for the Wigner functions. It means this is the first case when we can conclusively, faithfully decide about difference between different non-Gaussian states based just on the experimental measurement. Of course, it was very tempting to test this hierarchy. Means this is what we somehow did in OLOMOUC here. We were not able to prepare the FOCK-STATEs, but we were able to prepare states which had the statistics equivalent to the photon statistics equivalent to the FOCK-STATEs. And we tested them. And these states, they were able to show this quantum non-Gaussianity up to third order of the hierarchy. Means we were able to confirm genuine quantum non-Gaussianity of states with 3 photons, as you could see here. But this was the maximum what heralded sources with parametric down conversion were capable of. It means, yeah, we need quite improvement of these sources using possibly photon number resolving detectors, and we in general hope that optical technology will go from conditional state preparation more to deterministic state preparation, and yeah, then we could use that hierarchy for much higher photon numbers and test the quality of generated FOCK-STATEs. Actually, we somehow overcome that limit by beautiful step side, because we used the trapped ions experiments recently to go beyond that FOCK-STATE free, not for photons, but for phonons. They're anyway bosons. It means it's, yeah, it's still quite something for what we can apply that hierarchy. And if you want to hear more details, then just visit the poster of Lukáš Podhora on the same day. This hierarchy, it can be applied quite broadly to the sources which are basically from parametric down conversion, from optical parametric oscillators, but as well to the sources which are from quantum dots. Yeah, like these sources, they can still very much use the fact that we can apply the hierarchy for states with positive Wigner function. Yeah, I think this is quite nice. But as well, we can apply the hierarchy to another experimental platforms. As I mentioned, we can test FOCK-STATEs generated in trapped ion experiments. We can test phononic states by that hierarchy. But as well, we can apply this to quantum acoustics. It means to the phononic states of quite larger systems than are just single atoms. Means, yeah, I hope that this contribution to quantum non-Gaussianity will help experimentalists to improve their experimental setups, to see more clearly the important features of the FOCK-STATEs as basic elements of the superpositions which we need for the applications. But we didn't stop at that point. We as well thought, okay, once we actually test quantum non-Gaussian features of multi-photon states, we could look as well to more complex tasks, whether actually, for example, photon pairs, which we could generate, are simulable by two-mode Gaussian states. It means now the trivial states will be all possible two-mode Gaussian states, which you could imagine. Fortunately, when you solve this task, which is already by one level of the complexity more demanding than what I showed you at the last slides, fortunately, many times you find some simpler states, sometimes even two-mode squeeze states as the optimal states, as optimal Gaussian states. Means this helps you a lot to analyze the problems. And we, together with Lukáš Lachman, we succeeded really to find first quantum non-Gaussian test for photon coincidences. It means this is something a little bit higher type of the test comparing to the standard test when we measure photon cross-correlation function and decide about non-classicality of photon pairs based on that. And this is very interesting because already from 60s, we have sources in which we use a single atom and the emission of the photons from the cascade of that single atom. And these sources in this form or more modern form, when we use cascades, for example, in solid state quantum dot sources, they are in principle capable to show these, to demonstrate these quantum non-Gaussian photon coincidences. And this is right now of some intensive experimental collaboration if we will be able to see such quantum non-Gaussian coincidences. But when we talk about the multi-photon states, I would like to as well mention another approach which we pushed together with experimental team of Julien Laurent at LKB Paris, in which we tried to actually predict how well, in principle, statistics, photon statistics of multiple single photon states will allow us to, in principle, form arbitrary FOCK-STATE N. It means this task is that you have n times a little bit different copies of single photon states. You measure them very precisely, and then you apply all these measured photon statistics to computational quantifier, which allows you to predict whether these states are already so good that they will give you potentially FOCK-STATE n from that n replicas of single photon state. It means that procedure uses the process in the computer, but you can as well think about that in a more physical way, that it's like a linear network where in principle you could measure on all the outputs except the last one. And if you project all the outputs to the vacuum, then you kind of concentrate all that single photon states to just one output, and you test whether this output contains FOCK-STATE n when there were n single photon states at input. All right, we first analyzed that kind of quantifier theoretically, and we figure out quite interesting aspects. It was worked together with Peter Zapletal, which is now at VMPL Erlangen, and we realized that actually the dependency on minimum efficiency of that single photon source as a function of the number of that single photon states is actually quite nonlinear. That was first observation. But then there was as well a second observation that if the efficiency surpasses some threshold, then actually we can guarantee, at least numerically, that there is a chance to generate arbitrary FOCK-STATE from such a single photon state. It means we were quite surprised how such a simple task used to evaluate quality of single photon states gives us a very different perspective than what I described you before, or what we can actually learn out of the Wigner function, or what we can see when we apply HBT measurement and evaluate G2. Of course, we were quite interested whether current states could actually reach such very high FOCK-STATE capabilities. This was the title of that feature which we wanted to test it. And we picked some numbers from experimental papers and observed that, yeah, some of the experiments, they could reach FOCK-STATE capability 7. It means if you merge these signals from 7 single photon sources, you can go to the FOCK-STATE 7 and see really the 7 negativities of the Wigner function as it should be for that FOCK-STATE 7. But then we as well saw that other sources, probably a bit better, they could reach even twice larger FOCK-STATE capability. It means from 14 single photon states, you can approach in principle FOCK-STATE 14 with really 14 negative values of the Wigner function when you look to the cut of the Wigner function along the quadrature axis. It means, yeah, this was very stimulating, and fortunately Julian and his team agreed, and they were as well interested to test their single photon sources. The reason why that was important is that in the theory, we typically assume that our resources, here single photon states, are all basically identical. It means we kind of live in a symmetrical subspace of the wall Hilbert space. And that kind of life is comfortable. Many times you can calculate something more easily. Many times you can predict very good results, but actually in experiment, we always live outside that subspace. And that's quite important, and it's important to take this into account when we evaluate multi-copy protocols and when we evaluate basically multiple use of the resources. It means we did it for single photon states conditionally prepared from the parametric optical processes using very efficient single photon detectors at cryogenic temperature. And we realized really diversity of the possibilities. We saw that for some single photon states, we are very limited. We could go to the Fock-state capability 2. Even sometimes if we see negativity of the Wigner function just a little bit, it will not help us to bunch the photons and see higher Fock states at all. We could improve these sources, and by increasing the single photon component, we could go to Fock-state capability 3, 4. But then, as I said, when we start to improve it even more, there is like a sudden increase of the Fock-state capability. And at some point, we actually reach quite high Fock-state capability, 14, as we predicted in that theoretical papers. This is all nice. We know that we right now have already quite powerful single photon sources, at least at this experimental platform. But we notice as well one point which is very good to keep in mind. And that point is that when we look to the Wigner function profile of that constructed Fock-state 14 in our computer, and we compare that with the ideal Fock-state 14, which was just adequately attenuated, we saw more or less perfect correspondence between the cut of the Wigner function of the real experimental state and that approximation by attenuated Fock-state 14. But when we look to the distribution of Fock states, that picture changed quite dramatically. Because here, if you look to the multiphoton contribution 15, in a real experiment, there was a much, much larger contribution than actually in that ideal attenuated Fock-state 14, which fitted so well in that cut of the Wigner function. It means this is another argument in the favor of this previous hierarchy, which actually analyzes these statistics rather than the negativity of the Wigner function, because that hierarchy is very sensitive to this and allows you, therefore, to categorize your Fock states much better. All right, I think we are going to the end of the talk. It was just about these basic elements, which possibly all of or majority of the talks will as well use for quantum non-Gaussian physics. But we recently moved from the Fock states to really their superpositions. And we analyze various superposition states and their non-Gaussianity given by the amplitudes of the probabilities. And yeah, we hope that soon you will hear from us about new possibilities, how to test that. But we as well extensively investigate that other pole, that south pole, where we look for quantum non-Gaussian aspects of these more continuous superpositions of states with amplitudes of probabilities, which are exponents of higher powers of x than 2. And yeah, like there are already some examples of these nonlinear phase states, the JKP states, and I think they will grow much more, especially if we are able to prepare such states in experiments. And yeah, there are already few first experiments when these nonlinear phase states actually were observed. It means, and JKP states as well. It means I think this is a very prospective field for young researchers and PhD students because it's very new and very fresh. If you want to hear about some of our attempts from our youngest colleagues, then yeah, please visit posters 7 and 10 tomorrow, and you can talk with the young people about this. Our next targets, yeah, they are very diverse and many, but yeah, they basically go from one side of quantum non-Gaussianity, of photons, phonons, quantum non-Gaussian coincidences, but as well quantum non-Gaussian coherence and correlations. They go to ways how that things could help us to build optical gates for processing of quantum information, quantum applications, maybe at some point even for quantum computing. And through that, they as well continue to investigation of nonlinear, highly nonlinear quantum physics, where quantum non-Gaussian states actually appear very naturally as just outcomes of such a processes. It means there is no special way to basically think about them as we are used to right now. They just are ordinary outcomes, as now, for example, the squeeze states from optical parametric oscillator. It means this is the field which is very fresh, and I hope and we hope very much that it will grow very fast. All right, we as well we will try very much to enlarge the applications of all these states in all pillars of quantum technology, but as well beyond that in quantum thermodynamics and maybe new fields which will come. And for that, of course, we look very much for PhD students and postdocs. And we have a couple of the positions available already for the new center, which we just got from this year. Yeah, it's about quantum non-Gaussian coherence. It means it's pretty related subject. I think what is important here is actually that our field looks right now like that. We are building some picture of quantum non-Gaussian world, but we just have only few things in the puzzle, and yeah, we will see what will come up. It will be definitely interesting, definitely stimulating. There will be a lot of questions, a lot of debates, hopefully a lot of experiments. And yeah, I think this is my last slide. I would like to just wish you that you enjoy all these non-Gauss workshops. And yeah, I'm open in the last minutes for the questions.